Stephen Hancock. I'm actually from the University of Edinburgh. I'm working with Alta Technology on this project, but I'm at University of Edinburgh, which is where the spectroscopy facility is. So we are working on a future spaceborne LiDAR mission constellation concept with complete coverage, working particularly with places like the Fraunhofer Centre for Applied Photonics, UK Astronomy and Technology Centre, Alta, and Red Wave Labs as well. So I'm a remote sensing scientist, so I've started off talking about why we need the data, but I'll get on to the what we need to make the data possible in a minute. So I mainly work on vegetation remote sensing, and still to this day, the land use change and the growth of plants is the biggest uncertainty in the terrestrial carbon cycle. We just don't know quite how much they're sequestering as they grow, and when they're being chopped down and burnt, we're not quite sure how much is being emitted from it. It's a big unknown in monitoring and verification of carbon credits, that type of thing. Forest fires also very important for that, and biodiversity, nature credits, something that people are very interested in trying to monitor. Biodiversity, habitat structural complexity of forest drives that. Commercial forestry are also very interested in knowing when to harvest their timber, and there's more work recently showing how mental well-being is linked to green space, biodiversity, habitat access, that type of thing. So we've been, I worked on the JEDI mission, the NASA JEDI mission, which is a fantastic LiDAR just been turned off a year ago that fires laser pulse down at the ground. And from that, you can measure the structure of the forest. You can work out where the ground is, measure the bare earth topography, measure the height above and the density of the forest. It's the best way for measuring biomass and structural complexity, which is a useful indicator of biodiversity. There's been lots of spaceborne LiDAR missions over the last few years, mainly led by NASA, but with ESA launching a few, and CNSA over in China launching one. Last year was a bad year for LiDARs, with 4 of them turned off, but there's more interest in future LiDARs. They're all providing unique data sets. The problem with them all is they have very, very sparse sampling down to the power requirements. I was really interested in that first talk. If you've got a way of upping the power of these instruments, you can increase the coverage potentially, depending on how much it costs to do that. This is an illustration of the JEDI mission, which is the densest sampling LiDAR there's been so far, as it goes across Milton Keynes in the UK. Every red dot is a measurement. Everything in between you have to infer via statistics. Leads to very large sampling areas, makes it very difficult to know the precise biomass, and particularly the biomass change between 2 sites. So LiDAR data is really useful. It's the best way for doing biomass bare topography. It allows flood modeling, biomass mapping, biodiversity mapping. The problem is there is no globally continuous LiDAR data set. There's no long-term LiDAR data set yet either. And that's adding to uncertainty in this. So what we've been trying to do as part of GLAMS, working with Alta and others, is to go from what the current satellite LiDARs do, try and increase the coverage, to try and give us that, reduce the sampling area, give us the annual repeat measurements. And the way we try and do that is through photonics, trying to maximize the laser and detector efficiencies. You can increase the amount of ground you illuminate, the more efficient those two are. For the platforms, try and maximize the payload power and telescope area per unit cost. You can always launch lots of big satellites, but it's very expensive. So you want to maximize all this per unit cost. And then through signal processing, try and reduce the energy requirements to try and get the best measurement back with the lowest amount of laser energy. There's a paper here if anyone wants to read about that. Very simple equation. You just maximize all the maximize the top 2, minimize the bottom 1. So what we're trying to do as part of GLAMS, working with Fraunhofer Centre for Applied Photonics, and I can see, I think, working with Coherent, I believe I saw a few people from there in the audience. We're trying to replace what the current satellite LiDARs use, which are these solid state lasers. This is the Homer laser from JEDI. It's about 30 centimeters long, about 5% efficient, very robust. Every satellite LiDAR so far has used a laser very similar to this. And we're trying to replace it with these small laser diodes. So there's one there, it's about 3 millimeters across in the red circle. The laser itself is 45% efficient. The driver is, we need to improve the efficiency of that a bit. The downside of those, they have much lower peak powers. So having to do lots of signal processing to try and get a decent measurement with this more efficient, smaller, lighter, cheaper laser. We were looking at using, on the left there is what the current LiDARs do, and they have tens of kilowatts of instantaneous power, something these laser diodes can never achieve. So we tried working at Ludwig Prada, came up with the idea of using pulse compressed LiDAR, very much like a radar, Unfortunately, it didn't quite work. You ended up with too many artifacts to try and see the ground under trees. But what we're trying to do now is a pulse train. So one of these on firing lots of little shots at the ground, keeping within the about 5-watt peak power requirement. That can build up over time a decent image of the ground, we think. Much more sensitive to background noise. This only works by night, but we think it will work from satellite. And there's a paper there by Hannes Hansen to explain that. We're also looking at trying to launch a constellation of these. Initially, we wanted to launch lots of small CubeSats. If you look at the numbers here, it shows how many satellites you need to cover the Earth once a year with a constellation of these. The satellites get bigger, you get more power, you get bigger telescopes, so you get more energy efficient, but the satellites get more expensive. And you can see here, you could do it with CubeSats, but you need tens of thousands, which would be prohibitively expensive. So it pushes towards a few larger satellites. We looked at using deployable optics as well, which would be brilliant. They would help us. However, the TRL is a little bit low, so we're sort of pausing that fight until later. And this is that paper there describing that by Chris Lowe, who was at Strathclyde. Now he works in the computer game industry, unfortunately. This here showing that as the satellites get even bigger, the power doesn't become the limit anymore. The instrument size and mass becomes the limitation. So we think we're settling on these 150 kilo class satellites, so medium-sized satellites. This is what we think a final GLAMIS satellite would look like. 150 kilo class satellite with, we hope, a 10% efficient laser and driver, 58% efficient detector, operating in the infrared, building up an image of the world. And if we have one of these, we think we can build an image of the Earth every 5 years. And if we had 6, we can build the image of the Earth every single year. This is beating through clouds as well. So what's needed? So the things in green we have funded, working with Altair, working with Fraunhofer and other groups. The things in black, we do not have funded yet. So very interested to hear if anyone has any solutions for these. We're trying to increase the laser diode efficiency. We're aiming for 10% with a driver at the moment, using short 5-amp pulses on that. We hopefully get the instrument designed in the next year or so. What we don't have is more efficient detectors. We're using off-the-shelf 58% efficient single photon counting detectors. If anyone has more efficient detectors that work in the near infrared, about 850 nanometers, we're very, very interested to hear that. Deployable optics, very interested in that, if that can be done high TRL. We thought we'd reduce the number of fights we'd have to start with. We also need to maximize the payload power and telescope area for a given satellite size. We think 150 kilo class satellite, and we want the maximum power for that. So really interested by the first talk, depending on how much that costs to subscribe to your beaming service. And we're trying to work up to launch, hopefully via an ESA Scout in the next 3 years is what we're aiming for, but all dependent on funding. So thank you very much for inviting us.